Hi, everybody. So here is Unit 5 that we will cover this year. This is a little bit more about elements and arrangement and some of the periodic, or excuse me, the atomic models carried on from our last unit. But this is more focused on the electrons and the energy and then the elements. We'll talk more about the periodic table. I know I said it last time, but this is another one of my favorite units. And anyway, I hope you think it's cool too. So this unit, we will start with talking about waves. And one of the things that physicists studied before they came up with some of the information that we'll talk about concerning elements and electrons were waves and how energy moves. And so a couple of things just to know about these waves is that there are different units, different characteristics that you can measure for each. One is frequency, which is the number of waves that go past a given point at a time in a time. And so it's like if you stood down at the end of a dock that extended out into the ocean, as the waves came in, if you stood there for a minute and counted each wave, that was going past you, you would determine the frequency. And we'll talk about it in a minute, but that is very related to energy. Wavelength is another wave characteristic, and that is the distance between two similar points on a wave. So either the, hang on, I'm trying to work with pins here. So either the crest or the trough. And so that is the wavelength between those two. And then you have the amplitude. And when we do the notes in class, I'll give you a little bit different picture. This is defined as the distance from the crest or the trough to the normal. And the normal is a line, and I probably won't draw it really perfectly here, but it is a line that just goes straight through the middle of the wave. And it is essentially where, if like you're thinking about like a pond, the normal is where the water would be when everything is calm. So it is where it would just settle to. And so the amplitude would be this distance, or you could do it down to the trough. So that is the amplitude of the wave. And again, like I said, what in the world does this seem to have to do with chemistry? But atoms and the movement of the electrons have been determined using these physics properties and the calculations that go with that. Okay, so energy. So this is the part that will start to make it feel a little bit more like we're talking about chemistry, because the electrons are an energy source basically with their charge. So anyway, first things first, waves do not carry energy, they transmit it, which essentially means that the energy just moves through the substance. What you see, like the waves out on the ocean, that is energy moving through those molecules of water. The molecules of water themselves don't move. They just stay in place and kind of move up and go back down as the wave passes through them. So they are simply a way for the energy, something for the energy to move through. And the amount of energy determines the height of the wave, the amplitude, and also the number of waves. A couple of relationships to know. This is one of those things you might see like on ACT tests, inverse and direct relationships. Frequency and wavelength have an inverse relationship, which means that if frequency is increasing, wavelength is decreasing, vice versa. And so you can, if your waves are closer together, then you can get more waves in. So smaller wavelength, higher number for your frequency. And then frequency and energy have a direct relationship. So if more energy is put into the substance, so into the ocean, into the water, then you will see more waves. So that would be your frequency. Okay, so these two words, this inverse and the direct relationship, again, are just things I want you to know for this unit, but also be aware that you'll see them in other subjects too. Okay, so now a little bit more about light. Light, as you probably know, that when it is bent or refracted, or when you look at it through a crystal or a prism, it is separated out into its different frequencies. And this is where we get the Roy G. Biv color spectrum. And so each color has a different frequency that is associated with it, which essentially means it has a different amount of energy that is associated with it. And so starting over at the red end, these are the non-ionizing energies, so harmless, safe amounts of energy. And then as you move across, you get down to the violet end, and this is ionizing. These are the big energies, the stuff that we just talked about that can actually do harm. Gamma rays, of course, X-rays. And so if you're looking at this spectrum, and if we could see it in waveform, and I'll try and draw this, it's kind of hard on this little screen, you would see something over here starting at the red end with low frequency, high wavelength, and low energy. So you would have this kind of easy small waves, and then as you moved, they would gradually get closer and closer together until you get to the end and it's much higher energy. And so over here you have very low energy, low, I'll just draw an F for it, low frequency, but a very high wavelength. And the opposite on this other side, much higher frequency, which means much higher energy, but a very low wavelength. Now, to us, again, what in the world does this have to do with chemistry? But when studying this, you are studying actual energy, and remember, energy is involved in all of the atoms and the electrons. So one other thing just to know about light is that very often you will hear it described as traveling in photons, and photons are bundles. And so light has this very distinctive characteristic of being able to be described in waves, but also in bundles. And so a man named, I believe it was Max Planck, came up with this, his constant, which is that 6.6262 number down there, times the frequency, and that could help you determine the energy in that particular light. And so as long as you had, as long as you can figure frequency, then you could determine the energy. And again, to us, maybe not that big a deal, but some other people use that to figure out more stuff about the atom. Okay, so here's one of those guys. So a man named Niels Bohr, there he is on your screen, proposed that all of this energy could be related to electrons for an atom. So remember, up to this point, we were dealing with Ernst Rutherford's model, and we had the nucleus in the middle, lots of space in between, but then the electrons were just kind of all over the place. And Niels looked at light, and he said, well, light is put into these levels, is quantized, that word up there. And he said, well, if light contains these specific amounts of energy, then if we can figure out some things about light and atoms, and look at some things in a different way, then we could maybe do a little bit more with the electrons. So he proposed that there are energy levels, and he based this on what we now know as the bright line spectra. And I don't have a picture of it on here. When you're in class, we'll actually look at some of these through some prisms and see these different things. But basically, when an electron is excited or given extra energy, heated up, or you add electric current to it, the electrons will absorb energy and jump up to a higher energy level. So around the nucleus, like this picture right here, this is one of his models. It's called the planetary model or solar system model. But when an electron is excited, it will jump up to the next higher energy level. So it will move away from the nucleus. It's not stable there, so it will have to go back to its original position. And when it does, energy is released. And if you're looking at it through a prism, if you have the equipment to do that, you will see energy in the form of light, and not only light, but very specific colors. Every element has its own, what they call bright line spectra, and it acts as a fingerprint for the element. In my classroom, on my periodic table, I have a little tiny periodic table, and has all these different colors in it for each element. That is the bright line spectra for those. And so it is it's one of the ways that they started organizing electrons. And so Bohr said that these electrons, he knew that these electrons were moving in different energy levels because of the colors that he saw. So now, Bohr's model was pretty simple. It only worked well if you were trying to figure out really small atoms, helium, hydrogen. So a group of 3 physicists were working on some other things involving light and electrons, and together their 3 concepts have come to be known or were put together to form the modern concept of the quantum mechanical model. And so we've got our 3 guys here. The top one is Louis de Broglie. And his concept, his theory is the dual nature of matter. And he said that light can act as particles and can act like light waves. And so he had this dual, so are they moving in waves? Or are they moving in bundles? And it turns out they're both. The bundles apply more to the electrons. The waves apply more to the actual light that you see. Then Werner Heisenberg, he's right there in the middle. He's this is kind of a funny one to me. He came up with the uncertainty principle, and he said we are just not going to be able to know everything. We're either going to know the speed of an electron or the location of an electron, but we can't know both at the same time. So so this is kind of some of that gray area. So like this is what is happening when it's moving between levels. And then Erwin Schrödinger, our last guy, he came up with the wave equation, and this can be used to predict where the electrons are most of the time. And so by this point, they had kind of coined the phrase the electron cloud. And so he said, using this equation, you can find the electron in that orbit or in that electron cloud the majority of the time. Okay, so now these things were put together, and they started coming up with some different wordings and different things. And one thing they added to Bohr's model were orbitals. And an orbital is a region of space in which an electron can be found 90% of the time. And they, again, through physics and calculation, looking at these different lights, using what they knew already about mass and the attraction between protons and electrons, they came up with 4 different orbitals, because an atom is not a flat object. It is a 3-dimensional object. And so the electrons aren't just moving in these circles right around the nucleus. They are moving in kind of figure 8 patterns, or even the blue one like a clover leaf, or even that really crazy one at the end, the purple, where it looks kind of like a flower. And when you put all of those different orbits together, that's where you get what we visualize sometimes, or what you see in drawings, as the atom. Now, they went through also and they looked at the different shapes and I forgot to say on the other page, but this SPDF here, those are the labels that they gave to the different shapes. S is circular, P is the figure 8, D is the kind of the 4 lobes, and then F is the flower. Anyway, and so they came up with, after doing more research on bigger elements with more electrons, they came up with a kind of a way to say where electrons were and how many there were. And so they based this on the first 4 energy levels. And so as we fill this out, you're going to have 4 energy levels. So just 1, 2, 3, 4 in that first little spot. And then as you go through, how many and what kind of orbitals are in those energy levels. And that first energy level is the closest one to the nucleus, so it's the most simple. And you have just an S orbital in that one. And there is only one of them present. There's only one type of orbit, and it is S. And it can hold a total of 2 electrons. Now that last column, the total number of electrons in the energy level, in this case it will be 2 because we only have this one energy level. In the second energy level, you have 2 types of orbitals. You have an S and a P. And for those, and you'll start to see a pattern here, you will still have one s orbital, and you will have 3 of the p orbitals. And then the total number, s is always going to hold 2, and the p orbital can hold, or p orbitals, I should say, can hold up to 6, which gives us a total of 8. And then moving on, the third energy level, you would have S, P, and D. And you would have 1 S, 3 P, and 5 D. And then you would have 2, 6, and 10 for what each one can hold. So the S can hold 2, the P orbitals together can hold 6, the D orbitals together can hold 10, and that would give us 18 total. And then last but not least, the fourth energy level has all of them, S, P, D, and F. So you'd have 1, 3, 5, and 7. And then you would have 2, 6, 10, and 14, and that would give you a grand total of 32. And so for our purposes, we won't really get into this really super complex electrons and where they are with the higher energy levels. But I do want you to know this is just a process for accounting for the electrons and where they are. Okay, so now our next thing, and this is where it really starts to get more about the atoms and the elements, is the concept of quantum numbers. And quantum numbers are used to tell where an electron is. So they're like the address of the electron. And the quantum numbers include the orbital. So is it in an S, P, D, or an F? The energy level, 1, 2, 3, 4. And then in some cases, we won't get into too much the orientation, or what they sometimes call the spin of, not the spin, excuse me, the plane that the orbital is in. So it can be X, Y, or Z, which kind of comes out and behind the two-dimensional plane. One thing to know is Pauli's exclusion principle, and he determined that electrons that are in the same orbital have to have opposite spin. And that is because they're both negative. You have 2 negative electrons, and so you don't want that. They won't travel together. They will be pushing each other away the whole time because of the negative, both having negative charges. And so they will move away from each other, and at at the bottom, sorry, you can't see my hands, can you? So they'll be moving away from each other, and at the bottom of their orbit, or whatever, they will come close to each other, but then they will push away and then keep going, and always going in opposite directions. And so that's the exclusion principle. If you put more in there, it will mess up that balance. Okay, so now 2 ways to tell where electrons are. An orbital filling diagram, which is less used, but still we're going to go over it, and then electron configuration, which is very very important in my opinion. And so they follow 2 rules: the off-valve principle, which says to fill the lowest energy level first, and Hund's rule, which says to fill each orbital with 1 electron before going back to the second electron. And when we do the example, that should make more sense. So first things first, here's the orbit filling diagram. And so you can see that we're just looking at 2 energy levels. The first energy level is this 1s, this one. And the second energy level is the 2, but remember it contains an s and a p orbit or orbitals in it. So when you are doing these, you have to know the atomic number, or excuse me, you have to know the number of electrons. So for our purposes here, we're just looking at neutral atoms. So if you know the atomic number of these, then you'll know the electron number. So hydrogen is element number 1, so we've got 1 electron. That 1 electron will go in the first energy level, and you always draw them as arrows to represent the spin. All right, helium has 2, it's the second element, so you'd have an up arrow and a down arrow. Lithium is 3, so you would have up, down, up. Beryllium is 4, up, down, up, down. Boron is 5, kind of gets repetitive, up down, up, down, up. Carbon is 6. Now here's the first one where we really have to apply Hund's rule. So we fill our first S, we fill our S, our second S, so that's an orbital. Then when we get to carbon, because it has 6, we have an up. Now we have one more arrow that we need to account for. This is where Hund's rule says put 1 electron in all the orbitals. So I'm going to put in the second one in this p orbit because they don't like to share. Electrons want to be as far apart from each other as possible. So nitrogen, you'd see the up, down, up, down. Then you would see up, up, up. And then with oxygen, we see we have to go back. So we have an up, down, and then you would have up, 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 and then go back for a down. Like I said, this one is, you'll see this sometimes in your textbook will show you an example of it. It just gets kind of repetitive and cumbersome. So electron configuration is more likely. And this one, I've got the rules kind of on this page. They may sound kind of confusing, but once we do the example, I think you'll be like, oh, okay, I can get this. So first off, you have to figure out the number of electrons. If it's neutral, then electrons equal the protons or the atomic number. If it's an ion, if it has a charge on it, you'll have to figure out the number of electrons, which is what we have already practiced, so you should know that one. Second, the subscript numbers on the chart, and this chart will be what I will give you, and you'll see it on the next page. They are accounting for the electrons in each energy level. And so you'll follow the arrows, add the subscripts, and you're going to match that to your number of electrons, and then you write the electron configuration. So let's do an example, and hopefully it will seem clearer. Okay, so this crazy arrow chart that you see on your screen, that is the off-bow process. This is like a little cheat sheet for you to use and follow the arrows, follow the rules that we just talked about, and be able to write the electron configuration. So if we're doing sodium, sodium is Na up there. It's a neutral atom in this case. It's number 11 on the periodic table, which means that we are dealing with 11 electrons. So you are going to start at the bottom. So you start down here at the bottom. Why aren't you writing? Oh, that's weird. Oh, there it goes. Okay, so you're going to start down here at the bottom and going to add subscripts as you go. And so you want your subscripts to equal to 11. So we know we're going to go through this first one. I've got 1s2, so I will write that down. And then I keep following the arrows, and I go up to 2s2. And so I have now accounted for 4 of my electrons by adding the 2 superscripts. I'm sorry, I've been saying that wrong the whole time. Superscripts. And then I follow my arrows again. I get over here to 2p6. So now 2 plus 2 plus 6 is 10. And so I need one more electron. So I get up here to this 3s1, or excuse me, 3s2, but I only need 1 to get to 11. So I would put 3s1. And so my superscripts should add up to my number of electrons. And you can do this for most elements. Again, it will get kind of tedious, and adding gets kind of old. But it is one of the ways that atoms and elements are designated. Okay, so now we're kind of bringing a little bit of the periodic table. One of the reasons, or the reason really, that the periodic table has such a weird shape. Why isn't it just like like rows and columns? The reason that you have some short columns and some tall columns is because of the electron configuration. And the electron configuration is very closely related to where the atom is on the periodic table. And the periodic table is technically divided into 4 blocks, and those blocks are the 4 orbitals, S, P, D, F. So they're all, I've got them labeled on there. And if you know the electron configuration of an atom, then you can tell where it is on the periodic table. And the way that you do that is looking at the last thing that you write down for the electron configuration. So if we go back to sodium, for sodium we just wrote down 1s2, oops, 2s2, 2p6, 3s1. Okay, so the last thing that we wrote down was S, which means that sodium is in that S group. And so if you were looking at a periodic table, sodium is like right here. It's right here. And not only does it tell you which section of the periodic table it is in, the 3 in front, so the 3 of the 3s1 tells you what row it is in. And sodium is in the third row. So if you looked again, it has hydrogen and lithium and then sodium. So it's the third row. And then the 1 tells you which column it is in. Sodium is in the first column. Okay, so it works with every element. It is super cool to me. Remember, I kind of geek out over some of this stuff. This is cool. The only flaw, I guess, in this whole process is that this middle section, so down here where I say D is for dorky, so D is dorky because you have to take into account that the 4th row on the periodic table would be the 3rd, like you would end it with a 3D something. Okay, so again, it's, you know, it's minor. It's really pretty cool that it works that way. Okay, so now another thing that you've done, and we'll talk, we'll go through it again, are Lewis dot structures, and these are just a representation to show where the outermost electrons are. So the last energy level is. This will be a lot more important in our next unit when we talk about bonding and molecule shapes and stuff. So Lewis dot structures use the symbol of the element, and they use the final level of the electron configuration. And so my example in here is sulfur, so that's why I have an S there. And sulfur, when you write out its electron configuration, oh, and I forgot to make all of these numbers subscripts, so those should all be subscripts on there. That stinks. Those are some subscripts, okay? So those are all going to add up to 16. Now, when I am writing my symbol, I look at the final energy level. So the final energy level is this 3. So if I have put in an S and a P, I'm going to look at both of those. And I add up my superscripts, and that's the number of dots that I'm going to use. So I would add 2 plus 4, and so I would end up with 6, and I would have 6. My pen doesn't like to make dots for some reason. 6 dots around my symbol, and that is representing the outermost electrons. Okay, so now moving on, the periodic table. So a little bit of history about the periodic table. The father of the periodic table is a man named Dmitri Mendeleev. He was a Russian chemist. He looks a little kind of raggedy there in that picture, but he is the person who got us started in the best way for organizing the elements. And there are other people who did this, other suggestions for how to group them. He put them into columns, and he put them in order of their increasing atomic mass. So as you go across the rows, you would see the mass getting larger. I know my copy is not great. It's kind of fuzzy to me, but you know, hopefully you can just kind of see the general pattern of it. And one thing he realized was looking at this, you know, the increase in atomic mass as he was going across, is that sometimes there were these big gaps, there were these big jumps from the mass of this known element to the next known element. And so he started to leave blanks in the periodic table, and sometimes he even predicted what they should find as far as the mass number went. And so some of these places on here where you see like he's just got numbers and doesn't have, you know, a letter, or, you know, doesn't have an element name or anything with it, he was predicting that there should be an element found with that mass number. And some of them he just left kind of blanks on there. It was huge. It was huge that he did this, because not only did it get people organized, it also gave kind of gave people something to look for, you know, instead of just trying to, you know, find something out of nothing. he kind of guided them. So our next guy is Henry Moseley, and he actually is considered the father of the modern periodic table, because once they discovered isotopes, they realized that this whole mass number thing it wasn't a bad idea really, but you just didn't have whole numbers. And so he said, well, let's put them in order of increasing atomic number. Remember, that's the number of protons, and that's the number that never changes. And so once you put them in this place, they're there for good. And so he basically just took Mendeleev's table and kind of rearranged it a little bit. Again, there were still some unknowns, but they could find them. And what they realized after they started organizing them was this concept of a periodic law, which says that the properties of the elements are periodic or are gradually increasing or decreasing functions of their atomic number. And basically what this is saying is that elements were similar to their surrounding elements. So changing the atomic number by 1, adding 1 more proton, would change some of the properties, but you would also still be easy to see that it was related to the other elements. And then as they figured out electron configuration and they started to see patterns there, they started to see these relationships. Okay, so now just periodic table stuff, just some things to know. First of all, the rows are called periods, so that's where we get periodic table from. And moving across from left to right, the atomic number increases. Each element has 1 more electron in its outer energy level. Sometimes these are called shells. That was terminology I always use. So if I say that, I want you to know I'm talking about energy levels. And the period number, or the row number, tells you the number of energy levels, in our case circles, that we could draw for the elements in that row or period. Now I'm using circles. I'm not using all of the loops and the lobes and the different shapes, just for simplicity. Okay, it's easier to represent this way. So if we are talking about row 2 on the periodic table, we have lithium here, and it has 3 total electrons. If we're talking about the atom, it's number 3. So and we'll talk more about how they figured it out. They figured that it's got 2 electrons here and 1 here. And that's actually back to the SPDF chart that we did. Beryllium is next, 4 electrons. So 1, 2, and then 1, 2. Boron, as you kind of jump across on the periodic table, has 5. 1, 2, 3, 4, 5. And I try and kind of spread them out because the electrons would want to be spread out. Carbon has 6. So 1, 2, and 3, 4, 5, 6. Nitrogen is 7. 1, 2, 3, 4, 5, 6, 7, and so on until you get all the way over to neon at the end, and it will have 2 on the inner circle and 8 on the outer. Okay, so now the columns, so up and down, these are called families or groups. There are 4 that I want you to know the specific name for. Group 1 are the alkali metals. Group 2 are the alkaline earth metals. Group 17, if we're talking about the columns, are the halogens. And group 18 are the noble gases. Now, I have also put on here an older designation. This is a Roman numeral, 1A, 2A, then 7A, and 8A. And I'll get to that in just a minute. I'm just going to go down my list here. But so elements in the same column have the same number of electrons in their outer shell. So for instance, everything in group 1 has 1 electron in its outer shell. So the last thing that you would write for everything in group 1, if you're doing electron configuration, would be something S1. So if you're talking about hydrogen, it would be 1s1. Lithium would be 2s1. Sodium, like we just did in our example, 3s1. Potassium, 4s1. So everything has the same number of electrons in that last energy level. Those electrons are valence electrons. And they're important because they are involved in bonding. And so we will definitely talk more about those. Now, back to the Roman numeral thing. If you see, and our periodic table in our classroom has this, if you see a Roman numeral with a capital A next to it, the Roman numeral tells you the number of valence electrons. There's multiple ways to figure it out from electron configuration and some of the things that we've talked about, but that's just another way. All right, some other things to know. The middle section is the transition metals, because their valence electrons can change. And then the lanthanide and actinide elements, they're that little bottom section, like the F section. They are known as the inner transition metals. Okay, now another big thing is oxidation number. This is labeled on my periodic table. When you guys get to your periodic table, you will label it on there also. We'll put all kinds of things on there, but this is a big one. The oxidation number is the charge that an atom is most likely to have when it's in a compound. And so the oxidation numbers come about by either gaining or losing electrons. Remember, we've talked about that. And the reason they do that now, which we haven't really talked about, the reason that atoms either gain or lose electrons is so that they can have an outer energy level like the noble gases, so the very last column. Because the noble gases all have, with the exception of helium, 8 electrons in their outer energy level, and that makes them the most stable. It's the reason that the noble gases don't form compounds with other elements naturally, and that's basically what the other elements, the other columns, are trying to get to. So if we're looking just at the tall columns, we're going to look at, we'll talk about transition more later, for group 1A, so the alkali metals, sodium has 1 electron in its outer shell, and it is very likely to lose that 1 electron. And remember, when it loses 1 electron, it becomes positive, and it becomes a positive 1. Magnesium is in the second column, so it has 2 electrons in its outer shell. It wants to lose those electrons, and when it does, it becomes a positive 2. Aluminum has 3, and it likes to lose those and become a positive 3. Now, if it's going to gain or lose, it will tend to lose electrons if it has a number of electrons closer to 0, which 1, 2, and 3 are closer to 0, so it will lose them. If they're closer to 8, it will tend to gain those electrons. So it's kind of what's easiest to lose just a few or gain just a few. Now, the exception, of course, is group 4, because it's right in the middle. 4 is right between 0 and 8. So this one depends on what the other elements are doing. If it is with an atom that tends to lose, then the group 4 element will gain. If it is with an element that tends to gain, then the group 4 element will lose. And so on our periodic table and on here, you can label it as a plus or minus 4. Then we've got the next kind of little set. And these guys now, so now we have 5 electrons in our outer shell. 5 is closer to 8, so it's going to gain, and it will gain 3 electrons. So you have a negative 3. Sodium has 6, so to get to 8 would gain 2, so become a negative 2. Chlorine has 7, so it would gain 1 and become a negative 1. Ar down there is argon, and it's already stable, so that's why it doesn't bond to anything. Okay, so there's no oxidation number for that. You wouldn't put anything. But these numbers, these positives and negatives, are the reason that atoms bond together. They are attracted to the opposite charge. So, one of the most common compounds that we talk about all the time is salt. Salt is made up of Na with its +1 and sodium, or Na, which is sodium, +1, chlorine, Cl, which is -1. So +1, -1 together, if they equal 0, they tend to form bonds and become a compound. Okay, we're almost done. So now, periodic trends. So this is, again, goes back to that periodic law. What are elements, what do we see as far as characteristics and their association with their location on the periodic table? So there are 4 trends. First one is atomic radius, and that is the size of the atom. So, how many energy levels, how big is it? And the trend is always related in terms of the group trend and the period trend. So the column trend and the row trend. So the group trend is that atomic radius tends to increase as you move from the top of the column down. So as you go towards the bottom of the column, you have bigger atoms, bigger atomic radius. The periodic trend is that they tend to get smaller as you move from left to right. And so to me, the easiest way to remember this is to look and see which atom has this trend, is like the biggest in this case, or has some of the other characteristics. So based on this trend, the biggest atom on the periodic table would be Fr, because it is at the bottom of the first column. And that first column, remember, it decreases as it moves away. So that means it would have to be the biggest. So I like to think of Fr as Big Frank. Okay, so Fr is the big element, or it matches that trend. All right, ionization energy. Ionization energy is how much energy does it take to remove an electron from an ion. So basically, how tightly is it holding its electrons? So ionization energy, IE there, decreases as you move down the group. So that means the elements at the top have higher ionization energy. And then it increases as you move from left to right. And so on the periodic table, the element that has the highest ionization energy is helium. Helium is He, and I like to think of this one as He-Man, because that was a cartoon when I was a kid, and He-Man was very strong, so he would be able to hold on to his electrons. Okay, now the next trend is electronegativity. This is the tendency for an atom to attract electrons to itself when it's chemically combined, and so electronegativity, decreases as you move down the group, so it's higher at the top of the column, and it increases as you move to the right. So that sounds very much like ionization energy, except this trend doesn't include the noble gases because they don't form bonds. That's the whole point of being noble. And so we're not talking about anything in that column, so we'd have to move to the halogens. And so the top of the halogen column is fluorine, F. And so I like to think of F as being attractive. So I call her, or it, I guess, Pretty Flo. Because you don't want to call her Pretty Flu, but Pretty Flo, Pretty Fluorine, and so she is very attractive to electrons. And then the last one, metallic properties. This is going to look the same as atomic radius, but so metallic properties, just metals. They have a shininess to them, a luster. They conduct things. They're shapeable. They lose electrons, and this trend increases as you go down to the bottom of a column, and then decreases as you move back to the left, which means it increases the other way. But this one again is Frank, so now he becomes Big Shiny Frank. So one of my students said one time they picture it like a really large man with like one of those kind of cheap suits that are kind of shiny. Whatever helps you. And then I just listed down there some non-metallic properties, basically the opposite. And so, things that are dull, not shiny, poor conductors, they're brittle, those kinds of things would be non-metallic. Okay, whew, we made it. So now ionization energies, they can be used to determine some things about the atom, and that's just the ionization energy is actually the energy needed to remove an electron from an atom, because that's how tightly they're holding on. And it has been determined that it takes much less energy to remove an outer shell electron than a core electron. So on my picture here, so this outer shell electron is only going to take, about 500 kilojoules, where as you move in one energy level, it's going to take almost 5,000. So where you see these big jumps is where you can determine where do we go from outer shell to inner shell. So my question's down there, how many electrons are in the outer shell of an element with ionization energies of? And so you want to look for where you have the biggest gap, where you have the biggest increase. And so for this first one, that biggest increase, the big jump, is between the second and third. So how many electrons are in the outer shell? 2, because it took me that much to remove those 2. And then for that second one, you'll look for, again, the biggest gap. So the biggest gap you should see is between the 5th and the 6th. And so this one has 5 electrons in the outer shell. Whew, that was a lot, and I went fast. And so, listen to this as many times as you want. Ask me questions in class. Just let me know. Let me know how you're doing.